In older lessons, we've looked at ways in which we can distinguish between different classes of carbon compounds. For example, we know that carboxylic acids, with the co-functional group, can be identified by its reaction with sodium carbonate, as this produces a salt, water, and carbon dioxide gas. The CO2 can then be identified by bubbling it through lime water to produce a milky white precipitate. Alkenes and alkanes can also be distinguished by using the bromine water test, as only unsaturated hydrocarbons like hexene can have the reactive double bond open up and undergo an addition reaction. Well, that's a simple version. Alcohols, well, primary and secondary versus tertiary alcohols, could also be distinguished through their reactions with acidified permanganate. Primary and secondary alcohols like propanol can be oxidized by permanganate, changing the purple color permanganate ion into a colorless manganese ion, which can then turn brown if manganese is oxidized into manganese oxide. However, alcohols can also be distinguished by their reaction with sodium metal. If a small piece of sodium is dropped into an alcohol like ethanol, it reacts steadily, producing bubbles of hydrogen gas and a solution of colorless sodium ethoxide. The ethoxide, that is the anion, is known as an alkoxide. If the unreacted ethanol is carefully evaporated from the solution, you should be left with a solid sodium ethoxide. Color is a bit like slightly burnt melted cheese. However, being an ionic compound, this readily dissolves in water, where the alkoxide ion behaves as a Bronsted-Lowry base, accepting hydrogen ions, forming the original alcohol and producing hydroxide ions. It's worth noting that primary, secondary, and tertiary alcohols can be distinguished by the production of hydrogen gas. Primary alcohols produce hydrogen the fastest, and so on for the secondary and tertiary alcohols.